Marek. Our next speaker, we've seen him before this morning. It's Maxime Remy from the firm PAC. It's a company which is active in the field of wastewater treatment and water treatment. He will tell us about the effect of low dosage of activated carbon on the performance of membrane bioreactors. So I would like to give him the word now.
Well, at this time I will not present my work with PAC. I will present my work at Wetsuit with PAC, but powdered activated carbon. In this case, that's what I did during my PhD thesis. That's my just an overview on the work I've been doing then. I will skip the presentation, the broad presentation of membrane bioreactor, because we already had it this morning. But this time I will focus more on the membrane fouling. So membrane fouling can be defined as the process which results in a lower performance of the membrane because of the deposition of basically foulants on the membrane surface inside the membrane or blocking the pores. It's a complex mechanism with which can be set aside in many different ones. You have pore blocking, you can have adsorption on the membrane, you can have concentration polarization, even though in membrane bioreactor this one doesn't play such a big role. You can have the cake layer deposition, but all those together are quite difficult to take apart from each other. So in this case we'll try to find possible answers to fouling by design of membrane bioreactors. What are the parameters we can play in the membrane bioreactor in order to get the fouling as low as possible? We can optimize the membrane. That has been shown already today with, by example, adding micro nanoparticles on top of the membrane, but you can also play with the pore size, the morphology of the pores, if they are like funnels or the other way around. Just by designing your pores, you can already play with what kind of fouling you will get, the porosity, the roughness, but that's not what I will present. Then you can optimize the membrane operation. You can, by moving if you reduce your flux, you will have less fouling. If you can have some shear, some air scouring, some better module design, some cleaning procedures, or for example, a very nice cleaning membrane configuration which goes downstream here, if you heard about it. The last one would be the optimization of the field properties. That is what I will focus on and what I've been focusing on. You can modify it by changing the sludge retention time, the suspended solids concentration, by also the wastewater characteristics will have an effect, but you can also add some additives to the sludge in order to make it more efficient. And this is what my thesis has been about. How I started with the Varsseveld STOA project on the first full-scale Dutch membrane bioreactor. During the startup, I've been following all the parameters of the biology. When I was going there and the operators were not that happy, it meant that there was a problem on fouling. Then I was happy because I would get interesting values. What I found from gathering all those values together, I found that the foulants are mostly the free polymers, and that flocculation would be an important, nice way in order to get them out of reach for the membrane and keeping them in the flux. So the conclusion of this research was that floc fragments are dominant within the fouling, and the flocculation would be a key mechanism in order to keep them within the flux. By doing back some literature research in order to find a way in order to improve this flocculation, you can add multivalent cations or other system, but I found that the internal structure of the flux can determine its strengths, and it's very important to have nice, good flux. So what I did, I decided to add some activated carbon in there, very tiny amount, 0.5 gram for a high sludge retention time, so that they stay with the sludge the whole time. What the idea was that they get integrated into the floc and they create like a sun grain for a pearl. You get your flock which grows on this activated carbon. It makes an inner structure stronger, and then your flock is less sensitive to shear. And with less shear at the membrane surface where you have the most shear, then it doesn't release the foulants. And we also use activated carbon because, yeah, if we get an extra removal of micropollutants, that's all beneficial. So in the first step, I did some tests on filterability. For that, I had two membrane bioreactors running in parallel. You can see them, they are there. And then we had this filterability setup. It's a bit dark here, but it's a filterability setup with recirculation from the membrane bioreactor towards the filtration setup. And this allows us to characterize the filtrability of the sludge with the critical flux. What we found is that the sludge with powdered activated carbon could reach a 10% higher critical flux. We had a lower gel deposition in the case of high filtration at high flux, and we also could run for a longer period at higher fluxes. Then we tried to discover why the powdered activated carbon works. We added it for the flux strength, but in literature, especially with using higher concentration, up to 5 grams per liter of activated carbon, you can also find some other effects. One of them is the deposition of a less compressible cake layer at the membrane surface, because your activated carbon adds some strong particles inside your cake layer. In this ID, you would have a permeable cake layer. In our setup, we did not find cake layer deposition to be an important part with the fouling. So we took this one out. Then we looked at the improved scouring of the membrane. Once you have the gel deposited, the scouring is done by the bubbles, but if you add some strong particles next to that, then you might have a better scouring, like when you add some sand to clean with your water. In our case, we had all the pack particles were inside the flux. There were no free pack particles. So, and we also did some scouring tests, and it didn't really improve. So this was not the one. Adsorption of foulants. We did some tests. We indeed can adsorb polysaccharides protein to the activated carbon. Unfortunately, once it's adsorbed, we cannot really degrade it anymore. So given the low amount that we add to the sludge, this cannot explain the difference in fouling. If we could have had a dynamic adsorption degradation, that could have been an answer. But in this case, that was not the case. And once again, the activated carbon being inside the flux, they are not really available to adsorb the foulants. Then we checked improved flux strength. So we just started to mix the sludge and check the fouling. In this case, even when we increased the shear by an overhead mixer in both reactors, we found a much lower effect with a decrease of the critical flux for the sludge which has activated carbon in. So it came to the same conclusion. And here is, for example, a picture. But here is the pack particle, and you can see the flux coming towards here. We had flagellates in the reactor without pack. The flagellates are on the outside of the flux. When you add some pack, you see them going towards the inside. So yeah, the mechanism was improved flux strength. That's good. That's why we started to use it in the first place. So now I will present you following the reactor, because we found that there was improved filterability. We started to get an idea on why that was the case, but we also wanted to check what would be the effect on the other parameters of the membrane bioreactor. Filterability is not everything. So here is again the membrane bioreactor. We had two membrane bioreactor running in parallel, both with 50 days of sludge retention time. They were 85 liters reactor with about 10 hours of retention time. So we had 200 liters per day per reactor of produced permeate. We ran it for almost 1 year. And we were running on real municipal wastewater. Both of them had the same membrane and the same wastewater at the same time. They were both encountering the same variation in the temperature and in the concentration. So first on the membrane fouling, we were running the reactors at 43.5 liters per square meter per hour. And then what we could find in the case is that the sustainable filtration time, which is the time between cleanings in average, was of 55 days with the activated carbon compared to 32 days without. Then we started to increase the flux by removing membranes in order not to change the hydraulic retention time. Then we managed to run for clearly longer time at higher fluxes. And then when we started to go crazy and go up to almost 90 liters per square meter per hour, then they were both fouling. But the one with activated carbon, we had a gel deposition on the membrane surface, and this gel was easier to remove. And it was also less because we started to measure it in terms of polysaccharides and COD, and we had a 3 times lower amount of gel deposited. Also to remove it, we used a little sprayer, and the distance between the sprayer and the membrane had to be twice as low in order to remove the same amount. So we found that it was easier to remove. Then, so the fouling it worked. Then we started to look at the treatment performances because adding activated carbon could lead to better efficiency. We found a slight but consistent increase in the permeate quality. The difference is only 10 to 11% difference in different parameters. But given the high variation in the wastewater, we always had this difference. Always the one with PAC always had a slighter, better permeate quality. Also, we did LCOCD analysis of the COD, and we found it to be very strong in humics. That's in Leeuwarden, we have a lot of humics. Then we started to look at the micropollutants removal. The black bars are the one with activated carbon, the gray one are without. On the selection of organic micropollutants, we found some effects, but that's not yet to the end. We still, if we want to remove them, we still would need the post-treatment. Then we looked at the sludge properties. The suspended solids concentration was 0.5 gram extra with the one with activated carbon. That corresponds to the extra 0.5 gram of activated carbon. So that was fine. Then the particle size distribution, we had a higher average particle size for the membrane with activated carbon. Then we found a 45% lower sludge volumetric index. This, you don't really see it, but this one goes all the way there, and the other one there. The sludge with PAC was found to be much more compact, better settleable. In a membrane bioreactor, settleability is not one of the determining factors because you don't need your sludge to settle. But adding PAC creates stronger flux, more compact, and also better settleable. We found an 11% higher oxygen transfer with the activated carbon. Literature, recent literature has been linking the sludge volumetric index with the oxygen transfer, so that was also what we found. Then we also found a decreased sludge viscosity. That's the dynamic viscosity of both sludge. Again, the gray is without PAC, the black is with PAC. We found a lower viscosity of the sludge with PAC, but you also find it that it's less shear thinning. It's so when you don't add a lot of shear, your sludge doesn't get much more viscous, which is the case without PAC. So again, more compact flows and less sensitive to shear, less fluffy at the end. So then we did some tests because we know that in membrane bioreactor, when you have a salt peak or at one moment a low temperature, then you can have a high increase in fouling at once. We wanted to see if these stronger flux are also stronger in case of low temperature or high salt concentration. So we wanted to see if it also makes your reactor more robust for operation. We did find a better by adding 10 milliequivalent of salt in the water at once, keeping the filtration. The bottom one is the run test without the salt. The one that goes up is the one with salt. The one without pack, well, was more fouling without the salt, but then with the salt, we found a much higher effect on the filtrability. Then we tried to add a lot of salt to it to see what gets released. We found a much lower release of foulants at extremely high salinity for the sludge without activated carbon. And then we did again the critical flux measurements, and then we started to put the filtrability setup in an ice bath in order to decrease the temperature of the sludge at that point. And what we found is that the sludge with activated carbon, the critical flux decreased slightly with a decreased temperature. But the one without activated carbon, we found a big dip with much lower filtrability at lower temperature. So activated carbon, in this case, does make the sludge less sensitive to shear. So the conclusion, we could find improved sustainable filtration time at 70%, so without increasing the flux, but just by running at the same flux, and you can run much longer between the cleanings. That is one advantage. Then you have the possibility to increase the sustainable flux if you want. For it makes it again more robust in case of peak loads. You have a slight but consistent improvement of the permeate quality. The increased oxygen transfer by 11% is very interesting because in wastewater treatment plants, the aeration, the cost in order to put your air towards your blower is a big chunk of the economy of the energy costs. So if you can increase your oxygen transfer, it means that you need to provide less air to get the same oxygen towards the sludge. That's an interesting effect. There were some links found in between the sludge volumetric index and the dewaterability. So we suspect a better dewaterability of the sludge with activated carbon. Again, excess sludge treatment is also an important cost in the wastewater treatment. So if you have less sludge to treat in volume, that's also beneficial. You have a slightly improved removal of organic micropollutants. It's not as good as we could have hoped. So maybe that activated carbon is not necessary, but just powdered carbon, that we could again decrease the costs. You have improved resistance against stress, so it makes our membrane bioreactor much more robust. And then you have extra cost of below 1 euro cent per cubic meter of treated water, thanks to the long retention time and the low concentration. And I think that's it. Yeah.
Thank you very much. Well, before going into details, one thing I learned about this presentation is that Varsseveld is not only the birthplace of the famous soccer coach Guus Hiddink, but also the place where the first MBR in the Netherlands was built. So that was one thing that struck me.